For the first generation of automobiles that ever designed, such as the Ford Model T, ethanol was a fuel. Now ethanol is used as a fuel for race cars, and researchers actually find that race cars filled with ethanol actually perform better than race cars filled with gasoline. Ethanol can also be used to power aircrafts. This is a picture I took recently for a small airplane that is powered by cellulosic ethanol. This lecture discusses cellulosic ethanol. Cellulosic biomass is available in a broad area. The major feedstock for cellulosic biomass include corn stover, switchgrass, miscanthus, and other dedicated energy crops. According to a report produced by DOE in 2005, crop residue can provide about 1/3 of cellulosic biomass. Another third of cellulosic biomass can be from dedicated energy crops. Other agriculture residues, forest residues, and urban wood waste can provide another third of cellulosic biomass. This is the geographical distribution of cellulosic biomass resources in the United States, produced by NREL. Cellulosic biomass is concentrated in the Corn Belt. What makes cellulosic ethanol different is that yeast cannot digest the lignin. Yeast can only digest the cellulose, but cellulose is covered by lignin and hemicellulose. Cellulosic ethanol production have to go through multiple pretreatment processes to separate lignin from hemicellulose and cellulose. Once cellulose is separated from lignin, the fermentation process is similar. In some of the co-fermentation processes, genetic modified yeast can digest both cellulose and hemicellulose to increase ethanol yield. Cellulosic ethanol has the potential to increase fuel productivity relative to starch-based ethanol. For every acre of land, biomass productivity for cellulosic biomass is higher than corn. Fuel yield measured by gallon per ton is slightly lower for cellulosic ethanol, but the final fuel productivity as measured by gallon per acre can be much higher than corn ethanol, especially for cellulosic ethanol produced from grasses. In addition to the potential increase in fuel productivity, producing ethanol from cellulosic biomass also have additional benefit to soil quality and the agriculture land. This table compares woody biomass energy crops and the corn, wheat, soybean crop production system. The numbers in this table shows the reduction in agriculture intensity. For example, woody biomass and grasses can reduce land erosion for 12-fold and 125-fold. Woody biomass and grasses also can reduce the use of chemicals such as fertilizer, herbicides, insecticides, fungicide for a significant amount. The life cycle assessment suggests significant reduction in greenhouse gas emissions. In comparison with gasoline, cellulosic ethanol produced from forest residues can reduce GHG emissions for over 77%. Ethanol produced from farmed trees can reduce greenhouse gas emissions for over 98%. However, the cellulosic ethanol industry faces a lot of challenges. One of the most important barriers is high cost. An analysis of the cost for cellulosic ethanol production shows that the cost for enzymes is a major factor for driving the production cost. Feedstock cost is also significant. In addition, cellulosic ethanol requires a longer processing time that indicates higher operational cost and larger spaces are needed, which all end up being higher cost. An analysis by Kazi in 2010 suggests that the retail price for cellulosic ethanol is not competitive. The cost for cellulosic ethanol declines in the future, but is still not competitive. Such as the Ford Model T